Good afternoon, guys. Welcome to 765 what's the name? Machine learning and data analytics and machine learning for the second online class. So today we're gonna continue the LDA, linear discriminant. Not here, sorry. The linear discriminant analysis. Let me share my screen and meanwhile stop the video here. Share. Okay. So in the last time, let's briefly have a review. We introduced the model of LDA, and also anything this way, and then it's equivalent to determine by our linear. Let me put the annotate here. Spotlight. Okay, now you can see my annotate, right? Okay, then we say that this one is equivalent to define a linear discriminant function and determine, by the Bayes rule. This is very simple, and we estimated the prior distribution, the mean, and the sigma, which is the common variance matrix, by this way. Here again, the reason minus m is because I have m classes. Okay, it's a common matrix, common covariance matrix that I'm gonna estimate for all classes. And then we introduced if LDA has only two cases, then it's simpler. It's gonna be simpler because I only need to see whether this one is greater than the other one. If yes, then I'm gonna predict it as label 2. Why? Because in this case, I'm gonna say that this one, K is label 2, okay? This is greater than or equal to that one. Because in this case, I'm gonna have this, the value of here, of this number greater than or equal to 1, then by log, it's gonna be greater than 0, right? Okay, let me go back, clear. And further, we introduced that this one is actually equivalent to the least square regression, so that it's okay, it's still safe, even if it seems that we estimate from a group information rather than point-wise information. And then we introduced a little bit about the generalized LDA, which is this one, okay? Just a linear classification, very regular linear classification. And we showed a geometric interpretation. And then we introduced the QDA, the quadratic discriminant analysis, which is nothing but to drop the assumption that all classes share the same covariance matrix, so that I can have a sigma k here. Each class has its own covariance matrix. The thing is that it's gonna make this function to be quadratic, no longer linear anymore, and hence it's called QDA. And we showed the examples here, and also we showed computations for LDA and the QDA. The trick is by eigenvalue decomposition, so that I can make the things easier rather than brutally calculate this inverse matrix, which is going to be a very, very time-consuming work if the dimension of the, let's say, if the dimension of the matrix D is very, very high, the feature space, if the dimension is a high space, okay? Now, we're going to introduce a little bit about LDA versus logistic regression. After we are going to go back here again. So through the LDA model, you may have found that it is really, really close to the logistic regression model. So this is the class notes for logistic regression. I open it, and you can clearly see. So here in LDA, we assumed in this way. Let me draw a box here. While in logistic regression, let me change the color. We, create a model in this way. It looks really similar. Just to change the beta to W. Everything looks really exactly the same. Good. But are they really the same? The truth is they are not. So there are mainly two differences between LDA and the logistic regression. Sorry, I should move this traditional here. Between the traditional LDA and LR, not the LDA and traditional LR. The first difference is that LDA has more assumptions, right? For example, LDA, traditional LDA I'm talking about, okay, needs to assume that all given probability or probability distribution given the class information as normal distributed, and also all covariance matrix, with respect to different classes equal to sigma. So this makes, LR logistic regression more general. However, if these assumptions are satisfied, actually you can see that the LDA is more powerful. Why? The main reason is because in the logistic regression, what did we do? So, let me clear the joins and then go to Spotlight. So what we did here, the modeling, classification modeling, is that yes, we did model it as a point-to-point, information, and then we'll blah 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 maximize the log likelihood. The problem is that actually what we're doing in the logistic regression is that we're maximizing here the conditional log likelihood, right? And we set a multi-nully distribution for y, and we do the job. By contrast, in LDA, we filter parameter by what? By maximizing the full log likelihood instead of the conditional log likelihood. So this is a key difference, because based on the joint function, joint density, which is in 6. 6 is here. Let me see where is 6. Here. That's what I'm talking about. From here, we can actually expand it in this way. Okay. This phi is nothing but a Gaussian density function. And this pi is, of course, the prior distribution. And then here we do, include the information of the prior. I'm talking about the px. Sorry, it's not the prior, it's the marginal distribution, or you can call it a support, the one in the denominator. This one does play a role. Why? Because if I have this one, I can accumulate it, and then I can write it in this way. Just a summation of all case. And this and this are very, very close, correlated. So it does involve parameters. Another interesting thing is that you can clearly see in the linear discriminant function, I define it in this way. Where? Here. And see here, plus log k. See it? So this tells you that yes, the log k will directly be considered in what? In your decision, because your decision is right to maximize the linear discriminant function. So it's directly there. However, in your logic regression, no, it is not directly affected. We kind of like drop it. Indirectly, we actually dropped it. Okay, so this is the first. Sorry, where it is. This is the first difference. The second difference is that LDA in practice can be used with relatively small sample sizes, mainly because when we estimate the parameters, the normal distribution parameters by 6 here, again 6, that's how we estimate the normal distributions. Remember in the last lecture, I actually also mentioned, as long as we know that they are normally distributed, this is always correct. Who cares? How many data you have? Of course, you don't want to have just one data, a relatively small sample size, let's say 20, 30, or even, yes, it works, very good. The problem is that if you do this for the LR, the logistic regression, you're gonna have trouble. Why? Because the logistic regression doesn't have such an assumption, right? So logistic regression here, what we did is, again, we use the multi-nully distribution. When class is 2, so it becomes the Bernoulli distribution, and we blah, 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 fit, the model, maximize the conditional log likelihood. So here, relatively, we need a large sample size. That's mainly the two reasons, the two differences between the LDA and LR. However, in practical operations, usually people do them together. And in many cases, you can see the difference, the results, prediction results between the LDA and the LR are not that huge. So that's a simple comparison between LDA and LR. Do you have any questions?
I have a question.
Yes.
So you said in the LR, we need a large sample size.
Relatively, yes, relatively large.
what is the reason? Do you want to approximate the multi-knowledge
No,
distribution?
multi-knowledge distribution because it's not to approximate. It's kind of like because you assumed or you modeled the y as a multi-knowledge distribution. Remember it?
Okay.
So in order to make it to be true.
So you mean the multi-knowledge distribution is valid if the sample size is large?
No, the main because is that in order to, partially you're correct. In order to make it reasonable, consider the case. Suppose I have only, let's say, consider two classes, okay, Bernoulli, and consider I flipped a coin for only 10 times. Would you really believe that, suppose I see 3 heads and 7 tails, would you really believe based on the 10 trials, you say that, okay, the percentage, the chance that I got a head is 30%. Would you believe it?
No.
Or not, right? You may believe it when it's really large. Of course, in terms, as we mentioned in the what, in the MLE.
You are talking about maximum likelihood function.
Yes.
Which is valid when the sample size is large. Yep.
Yeah. So
you have explained. You have explained about it already.
Yeah. So the same here, because I use the multi-knowledge distribution. How would you really trust that this model is correct, right? So I need a relatively larger sample size. However, in the LDA, I don't care. Why? Because I assume that all these conditional means conditional class samples follow normal distribution. If this assumption is correct, of course, I mean, who cares how, theoretically, even you have one data, theoretically, the way we estimate in 6 is correct. Theoretically, okay, although nobody's gonna really do it for one data, but indeed, the sample size, the training data size would be smaller if you train by LDA. Any other questions? Where are Arapa and Mabuba? Hello, are you there? Okay. Okay, so there's some very simple introduction about the difference. Now let's go back to the main topic today, which is a reduced rank LDA. This is a rank, actually dimension reduction technique. The main part of dimension reduction on the feature space of X will be introduced in PCA, and later you're gonna see this is really a special case of PCA, principal component analysis. However, here I think it's very important to let you already see it in terms of LDA. Why? Because LDA will be the last linear classification technique that I'm going to introduce in this class. After it, I'm going to introduce SVM, which is nonlinear. Okay. So first of all, we need to have a look at our calculation steps here. Where it is? Here. Okay, so here we apply the eigenvalue decomposition, and here I already corrected the typo there, and I rewrite it in this way. So after this way, you can see these two parts are equivalent. So that I have, for example, suppose this is B, I have BT times B. See it? It's kind of like a square. Okay, so and you know what? Usually if I have this kind of form, it means what? It means, forget about the mu, okay? Suppose mu is 0, to make my life easier, because mu is nothing but a shift. If I have this one, that means I'm gonna have a circle. You know why? I'm gonna have a circle. Let me ask you, y equal to x, I should say what? Let's say x squared equal to, let's say a number. What is the, let's say x squared plus y squared equal to 1, let's say. What is that? It's a circle, right?
It's a circle with the radius of 1.
Right. Okay. Now, if I have x squared over 4 plus y squared over 9 equal to 1, then you have what? You're going to have an ellipse, right? Yeah. So the same here. The key is that here, I no longer have this sigma inverse. Or you can say this sigma inverse equal to I. I is the identity matrix, okay? So that, yes, this is going to be a circle. And actually, by observing this one, the idea here is this. I wanna, I can already show you here. So the original normal distribution in 2 dimensions, okay? 2 dimensions, what I mean is the feature space, not the classes. Although here, indeed, I have only 2 classes. In the 2-dimensional feature space, I have x1, x2. It's gonna be an ellipse. Why ellipse? Because have a look at this structure for the normal distribution. I have a mu. Mu is kind of like the centroid here. And by the way, do you understand what is centroid? Centroid means the center, okay? The center of an ellipse, or let's say a circle or a sphere. So mu is the centroid, but sigma squared controls what? Controls how big these two, sides are. What I mean is this. Let me draw a line. This is to control how big this and this. These two axes are. And meanwhile, because we have covariance, remember? If we don't have covariance, what you're gonna see is a very beautiful ellipse like this way. If I have covariance, how to rotate it? Can I rotate this one? No, it doesn't let me. I want to rotate it. Okay, I cannot rotate. Let me use the MATLAB.
Oh,
let me use the
MATLAB. It's gonna be a rotated oval.
Yeah, I want to rotate this ellipse. Let's say. No. Anyway, forget about it. Let me use MATLAB. I cannot tolerate it. Wait. Let me go to Spotlight. Let me give me 1 second.
So it's gonna be something like a ball, isn't it?
No, it's not a ball. It's gonna be an ellipse. Okay, let's really write. What looks like
I
this
know
one? No,
a
I
ball.
don't like it.
A baseball. It's like a baseball, isn't it?
It's gonna be an ellipsoid. Let me show you. It's
no,
gonna be.
I mean the American football. Sorry, not baseball.
Okay. Let me generate the data. Then you're gonna see what I'm talking about. I'm gonna redo this example right here. I'm gonna code it. So haven't coded it for a long time. I'm gonna I remember I have 0, 0. So x is right in the center. Okay, I don't have a mu x here, and I remember my mu y is 4080 or whatever number, not a big deal. And sigma matrix is for 16 and 16100, for example. Okay, so I'm gonna show you different, sigmas, and you're gonna see what's gonna happen. That's really interesting. And I set n equal to 10,000, which is the number of simulations. Okay, so what I'm gonna do is I'm gonna generate the multi-variate normal distribution. Okay, here we go. Multi-normal. I cannot remember this command because here. Okay, so this is a command. Then I get it here, copy and paste, and I name it to be x, let's say. And then let me use mu x and sigma n, and I'm gonna do the same for y. But the difference is that I'm gonna use mu y here, okay? Then I'm gonna plot, and then let you see what does it really look like. It's gonna be really interesting. I'm gonna plot for the first, because in this case, the x is gonna be what? The x is gonna be let's say n times 2. N means 10,000, and the 2 means, because I have two features here, mu x and mu y. Okay, so that I'm gonna plot for the MATLAB command. This is gonna be all the axis coordinates, and the second one is gonna be the y coordinate, and I'm gonna use a small dot. Let me use hold on. And I need to make the axis equal. Otherwise, it's going to be something very different. How many of you use MATLAB here? Arap, you use MATLAB, right? Mahbub and Said, did you use MATLAB?
No, I'm using.
Yeah, Arap, I guess you know why I need to write this, right? Because if you don't write axis equal, it's going to be very ugly. Anyway, this is not a class for MATLAB, but let me just skip it. Okay, so let me simply just write it in this way. And let's see, let's run it, see what's going to happen. Okay, what is it called? Let's say, let me call it, for example, LDA. Let's say LDA 1, whatever. Okay, see it? The result is here. See it? They are really two ellipses. Okay, so and this mu here for this point, that's in the middle. You can see 0 and 0. And this mu is what? This mu is 40 and 80. See it? Now let's see. What if I have the third one? Okay, for example, I keep it to be hold on And let's say I have the third one, and I change my sigma and mu's.
So here in this shape, do you have my voice?
Yes, yes.
So in this shape, it means we have two features because it's in the two-dimensional space.
Yes, you're correct. We have two features and two classes. These two
So
are the two classes.
If it becomes three features, it's gonna be in
3D.
three-dimensional.
It's gonna be 3D. I don't want to give trouble to my life, so I'm not gonna draw 3D.
Oh, okay, okay.
Okay, so this is
Okay.
2D. I have only two features, but here I have two classes. I'm gonna build a third class, but I'm gonna make a different sigma, and I'm gonna show you why it's gonna be different, how it looks like. And let me see, put a Z here.
So the number of dimensions is the number of classes or the number of features?
Features. I'm talking about feature space. Here,
because
I'm talking about feature. Because class space, you cannot ignore it. You know.
You just said class. I thought it's a class.
I said a class? No. These, I have two classes. You know, you see what I mean? For example, if a point is here, then you're going to predict to be this class.
Okay.
Right?
I get it.
But the 2D, because here I only have X and Y. Okay. Of course, you can have 10D, but you cannot draw. You can also have 3D, but I don't want to give my life trouble. Something trouble. So that I'm gonna ignore it. Okay. In this case, let me build the sigma to be this. Okay. I don't have any covariance. The covariance is 0. So this tells you. Okay. Let me write it here in the MATLAB, the command window. Suppose I have Z equals, let's say, sigma Z equal to, for example, 4, 0, 0, 10. What I mean is this, a matrix in this way. Okay, this is a MATLAB command. For most software, it's the same. Actually, APP the same. And then I'm gonna make this one, the sigma Z, in this way. Now I'm gonna generate the Z. Z equal to mu Z and sigma Z here. And I'm gonna plot this as well. And you're gonna see what's gonna happen. It's gonna be really interesting. Okay, run it again. Where's my plot? See it? Get a point? And then to something interesting. Well, it may be too small. How about this? Let me make it to be 100. Okay. See it? See this one? Why? You see there's no rotation here. See it? So what if I'm gonna change it to be, let's say 10, let's say 100 versus 10, for example. You know what's gonna happen? This one will be flat in this way. Okay, let's do it. See it? Because I use the hold on so that the previous plot is still here. See, it becomes this way. Okay, so what if let me close it. Do you know what if I write it in this way? What's gonna be for this one? It's gonna be a circle. See it? Circle. Now you understand for the normal distribution, what does sigma really mean? Okay. Now the thing is that suppose we don't have Z. Let me delete this, or let me just comment it. Suppose we don't have this. Make my life easier. Okay. I originally have this. Let me ask you, how would you classify? Suppose I give you a dot, which is here, for example. Which class would you classify? You're going to classify to this one, right? The blue one. Why? Simple, because it's close. Very easy, right? Okay. So if something's here, you're going to classify to this. What if something here? It's relatively more difficult. See it? Okay. Now the thing is that is there a way I can take advantage of this centroid and say whichever is close to which centroid is closer, I'm going to classify to that one. That is my idea. You know what I mean? So I want to use this idea to make something interesting, which is let me see, which is here. What I want to do is first I want to sphere these two. I want to sphere these two classes. Sphere means that make them to be circles because this is 2D. And then you may ask me, so well, why don't you, for example, let's see, Suppose this is central, for example. So why don't you directly, for example, make the prediction? Well, why you have to sphere it, right? Because if I directly make prediction like this way, you cannot well use the centroid to represent the whole class. Why? Because the two directions are not balanced. You know what I mean? It's not uniformly. I want to make this multinomial distribution, sorry, use this, make this multi-variate Gaussian distribution to be a sphere, as what we just drew before as a Z. In this case, it's going to be what? It's going to be uniform, or let's say harmonious, so that you can indeed predict by your centroid. Okay? Now the question is how to make them to be spheres rather than, you know, like this ellipse. We're going to use exactly the, okay, clear again. Every time I have to clear. I hope they can make it automatic. Then I'm going to really use the idea of here. See, by doing, I'm going to use the idea of here. By doing this way, see, it's a sphere. Get a point? Why? Because my sigma here is I. See what I mean? It's a unit sphere even. Remember in my MATLAB code here, what I just wrote here, I use this one, right? And this is indeed a sphere, remember? And why is sphere? Simply because this is the variance of the first feature. This is the variance of the second feature. There's no covariance. And these two are equal, right? Because if I write it in this way, it's not going to be a sphere, remember? Let's do it again, okay? Let's uncomment it and run it. And come. See, it's not a sphere. Why? Because your x direction, the variance, I should say the first feature direction, the variance is 20. So it's smaller in this direction. But your vertical direction is 120. Yes.
I have a question.
Mm-hmm.
So you mean we use eigenvalue decomposition to convert a discriminant function to a sphere?
Not a discriminant function, but my data. I'm not doing for my discriminant function. This is my data. This is my original data. See my code? My code is just to simulate, right? This tells me that I have a sigma x and a sigma y, sorry, mu x and mu y, and I have a common sigma, right? That's our LDA setting. And this tells you that I'm going to randomly generate the normal distribution, multivariate normal distribution following the Gaussian with mu as equal to mu x and the sigma equal to sigma y data, so that I have this one and this one. And this one for the z, which is this one, the same. You see it? My purpose is that is there a way I can change the coordinate system to make all of them to be circle? That's the point.
Okay.
Why I want to do this? Because once they are circle, I can directly use centroid. So I no longer need to really consider all of them. I just need 3 points. 1, 2, 3. Game over. No, mission accomplished. You're not going to game over. You're going to win. You know? So it's really easy. You see the point? Then I'm asking, how can you make it? The key trick is here. I'm going to take advantage of this.
Eigenvalue decomposition.
Okay? Ignore the mu. I'm going to have this part.
Okay.
And I'm going to show you the proof why this is really correct. I'm going to use this part. By doing this part, I claim anything like this way, it's going to be a sphere. Again, let me, I know I've already mentioned it for twice, but this is really important. Again, here in the code here, this is sigma xx, this is sigma yy, meaning meaning the variance of the first feature, the variance of the second feature, right? These two determines how large these two directions are. Okay, what I'm talking about this, let me draw it. How large these two directions are. This is sigma xx and sigma yy. Then this covariance tells you how much you can rotate. Look at this. This is vertical, right? There's a rotation. These two number, here's 0. Then this tells you 0 rotation. There's no rotation. If I have some number here, I'm going to rotate the coordinate system, which means, for example, here, my coordinate system is going to be something like this way. See it? I do have a degree. I rotate it clockwise. I don't know how many degrees, kind of like 1 o'clock, something like this. See it? So this is the thing. Then from here, it tells me that as long as I do it this way, who cares what your sigma looks like? It's going to be an identity matrix. To this end, I'm going to code it. I'm going to operate it in this way. So I'm going to sphere the training data by this. for a given and the target data for a given x, I'm gonna do this, setting x star equals to d inverse of a half times vt. This d and the vt are from what? Are from the singular, sorry, from the eigenvalue decomposition to the sigma hat, to the sigma, okay, which is here, which is this. Because here I don't, it's a traditional LDA, I don't have a k, so I directly have sigma hat equals to v d vt, okay, and this v, both these are unitary, or let's say orthonormal matrix, representing the eigenvalue the eigenvectors, okay, the space of eigenvectors, space spanned by the eigenvectors. This D is a diagonal matrix indicating the eigenvalues, okay, clear? Now let's see. And after the sphere, all of them gonna be 3 circles. What I'm gonna do is that I'm gonna target, I'm gonna classify my target data by this way. So xt is, you know, the one transformed, and the mu t is actually the what? The centroid is this mu t, mu k, sorry, and it's gonna be calculated in this way, okay? And sorry guys, there's a typo here. It should be xt star, xi star. Sorry, it should not be xi, because xi is the data in the original space. Here I transform it. It should be xi star. Then it's going to be really the mu k star. Otherwise, it's going to be the mu k. There's something wrong. Make a star here. And this is something about the prior distribution. Then I'm going to predict it in this way. And I claim this prediction will be exactly the same as my previous prediction using this, my linear discriminant function, which is here. I claim these two. You know, that way is the same as this way. And then you may ask me, how do you know? I mean, first of all, why you claim that you make a transform like d negative half and then vt times x equal to x star. Then in this new x star system, everything gonna be a sphere. Why? Okay, I can prove it in this way. Very simple. Let's calculate the covariance matrix of x star. Here here x is RD, okay? This is a vector, not a matrix. I define it here as a vector. You know, I use capital X because it's a random variable, okay? And this D is, again, the feature space. I'm talking about the feature space, okay? So I have x star equal to this, right? This is the transformation that I defined here. See it? I define x star equal to this, okay? So for capital X, I'm gonna have this. Now let's calculate the covariance of this x star. The covariance of this x star, you see, D is a constant number, V is a constant number. The only random number is what? The x, right? Let me ask you, suppose x is one-dimensional, and the x, the covariance, as the variance as, let's say, a sigma square. What is the variance of ax, where a is a scalar? It's going to be
a square,
right? Sigma square, right?
Yep.
So the same here. These are what? These, I'm talking about this. All these are nothing but coefficients.
Oh, it's a matrix form.
Yeah, it doesn't matter. It doesn't matter. No difference. Matrix form. The only difference is that the matrix form, when you're gonna say square, it's gonna be something times t, something a times at. That's the difference.
Exactly.
Okay.
Yep.
So the same. I'm gonna make this part. I'm gonna keep this part here, and x becomes what? X becomes variance of x. Okay. And I'm gonna again have this part t. That's it. See it? This is the covariance. And then you just expand it, you know, make this Vt to be, remember, Vt equals to inverse of V. So Vtt equals V itself. And then you just combine items, do some calculation, you're gonna see, yes, the covariance equal to I. This tells you that, yes, it's gonna roll and make all of them to be circles. And the second step is I claim that, oops, here. This way is equivalent to the previous decision rule. Why it's equivalent? Okay, let's see it. Because, because in the new coordinate system, x star system, okay, after the transformation, my linear discriminant function becomes what? See? I just copy and paste, you know, this is the definition of a linear discriminant function. Let me open another one. I remember I opened it already. So in this way, I don't have to rotate. Make you guys dizzy. Let's see. That's all the reason because I don't have a whiteboard. So this is the same, exactly the same as this lecture. Okay, I'll open two again because to let you see it more clear or easier. I don't have to rotate. Like flip the pages like this way. Okay, so we're here. So you can see this linear discriminant function is exactly this. The difference is that I'm gonna put x star. Okay, I'm gonna do it in the transformed system rather than the original data system. So I plug in x star, then everything is going to be this way. And don't forget, we just calculated that the covariance of x star equal to I. Okay, we just got it. So I just plug in here. And then you're going to do some operations here. I made a trick that I minus this item and I plus this item. I minus this item. And I plus this item. Why did I do it? Because I want to make it to the norm form. Okay. Then after this, you just do some simple calculation. I'm not gonna show in detail here. This is really, really simple. You're gonna have something in this way. See it? Because this plus 2 plus this is nothing but a square. Again, square in the high dimensional space means something t times something. Okay. And then you have a look at here, and this equal to this. This is something really, really amazing. A very, very standard problem for convex programming. Why? Because here, you see, x star is given. I want to predict the label of x star. How would you predict it? How would you predict it? What are you going to do is you want to predict it by this way, right? You're going to find a case such that this linear discriminant function is maximized. Guys, how to make this one maximized? Isn't it simple? You're going to do what? You're going to choose the k, because this is a constant. This half of x star t x star is a constant.
Minimize by making the first part 0.
No, be careful. Your log pi, your log pi k. See it? With different k's, your log pi k's are different. To maximize this part, isn't it equivalent to minimize the inverse of this part, right? Okay, now what is the inverse of this part? You take the negative half out, then you're going to have this part minus 2 log pi k, which is here. See it? That's the reason why I claim maximize linear discriminant function under the transformed space is equivalent to minimize this, because here I take the negative half out, so it becomes this minus 2 log pi k. Okay, that's the reason why I claim from here. Where? That's come on. That's the reason why I can do in this way. See it? And I proved that this one is gonna really give you a sphere, and this one is actually equivalent to this. So exactly everything the same. You may still confuse, say, hey, can you really show me something? Show me an example. Sure, I can show you the example because yesterday I coded. So I think I can do it. Let me see. Let's forget about the z, okay? Because at the matter, I'm gonna make it a circle finally. Then I'm gonna do the eigenvalue decomposition. Let me take it here. Cannot remember the formula because here. Okay, I'm gonna take the eigenvalue decomposition. D equal to EIG of sigma. And then after getting the eigenvalue decomposition, so to make my life easier, I'm gonna have two classes here. One is x star, one is a y star, okay? So I'm gonna have x star equal to this formula. I'm gonna apply this formula, which is d to the power of negative half times v prime, vt, v prime, and times x. But don't give me 1 second. I remember I got a confusion about dimension here because your x dimension is 10,000 by 2. But here I do need a 2 something. So it's going to be x prime. And that's going to be a prime again. So this one makes this x star to be x prime, to be 10,000 by 2 again. And this gonna, let me see. Then I'm going to do the same for y. Y star equal to this. And this is the y star prime prime. And then I'm going to do the plot. Okay. Let me make it a bit more beautiful. For example, give a blue color to X class, give a red color to Y class, and I assume to see, let me close it. I assume to see something similar. Yes, I got it. See it? Interesting? See? This is the transformed space. This is also after transform. Nice. Question. Why this one is so good? You know, everything as an ellipse. You know, the ellipse is, you know, become the sphere. But this one, it comes from here to here. Is there anything wrong? Why? Because don't forget this, guys. My x, the centroid is 0, 0. Okay, but my y centroid is 40, 80. Get a point? It does have a mu. So doing this one, it just give you a rotation and also a condense of give you a condensed, let's say, coordinates, but it doesn't charge the shift, or let's say it doesn't charge for the centroid. That's the reason why it's going to be in this way. But no worry, there's no difference. Why? Because for your target data, it's going to be in this way as well. For example, if a data is here, then after your transformation, it's going to be here. So something closer here is going to still be closer here. Okay. So in this way, yes, I really made it. I really made these two. Oops, where? I really verified, I should say. I really verified. First, this one's gonna sphere it, and the second, this one, I'm gonna do the classification, which is equivalent, proved to be equivalent here. Okay. Now the thing is that this still seems, I mean, pretty similar to the method that we discussed in section 5 point. Sorry, I think section 3.3 which in section 3, right? I mean, well, you did change the coordinate system, or let's say you did make a transformed form, but in terms of calculation, what's the difference? It's beautiful, but why you claim this is useful? Or what's the point here, right? The point is not just by calculation itself, but by the geometric interpretation. For my convenience, I'm gonna directly come here, use this graph. They're the same, actually. Okay, and have a look at here. So the dimension here is 2D, right? A 2D space, because I have, I mean, x, y, and x2. Then have a look at here. Suppose now you can ignore, you know, these two ellipses. Why? Because all the data information has already been here, be these two spheres. And because it's a sphere, so I can equivalently make everything in a centroid. Now, I want to kind of like make prediction on the data to see which one is closer. And there's one point I need to really emphasize here. Be careful, strictly, I still need to consider this one. Okay, it's a prior distribution of the classes, but I assume this pi is uniformly distributed. In other words, here we go. In other words, if the prior k has pi k equal to 1 over k for any k, so it's uniformly distributed, I can just simply ignore this part, right? Because any class is gonna give you the same number. Okay. Under
so it's just
yes.
It's just classified to the
closest
classified to the class which is the closer to the
centroid. Yes. So for example, if I have transformed target data, for example, it's here. Suppose it's here. Okay. Then if it's let me draw it. Suppose it is let me make it in this way. Let's see how ugly it is. Well, not too ugly. Suppose my data is here, then I'm gonna classify to here. Suppose it's here, then I'm gonna classify to here. Right? Very simple. Okay. Yep. Now an interesting thing is, you know what? I actually don't really need a 2D. I actually only need a 1D. For example, the 1D is this yellow line. Why? Because suppose I have a data point here. Let me change the color. Let's say use a pink color. Suppose, let me make it here. And hey, have a look at the projection. Where's my, okay. My projection of this one.
You can project it on the line.
Yes, see here? It's here. Question, which one is closer? This is closer to this one, right? So I'm gonna predict it to yellow, to red, right? Or if, let's say, I have a point which is here, for example, then similar, I'm gonna project this point to this line. And in other words, I don't need a 2D, I only need a 1D, which is the coordinate in this line. That's it. See it? This is the key why we need to explore this. And then why I spent so much time on this, I want you guys to really understand this. This is a very, very beautiful idea. And this is extremely important. Why? Because here I have 2D, right? 2D means, again, feature dimensions, okay? Feature. What if I have two classes and I have 100 of these? Guys, do believe even if I have 100 of these, I only need one line. One line. What does it mean? That means that I can reduce the feature dimensions from 100 to 1. How important it is, I don't need to explain. You guys are PhD students, you all know it, right? So that's a critical, that could be, I should say, that could be a critical reduction. See the point? However, be careful. Let me still reduce this one, clear. Be careful. The line coordinate doesn't have to be this line. I mean, you just connect these 2 points. Doesn't have to be, okay? This is just an example. For example, you can use this line. The same. Why? Because if I use this line as the 1D dimension, the 1D system, what I'm gonna do is this. I'm gonna first project Y. The same color. Clear. Let me make it a bit further. Let's say for example this line. Okay. Then the first thing that I'm gonna do is I'm gonna project my coordinates, my centroid here to these points, right? And then, so this is the centroid for this the red sphere. This is centroid for the blue sphere. Then suppose I have a given point. Suppose, for example, it's here. For example, I'm gonna do the same. I'm gonna project it to this this pink coordinate system. And clearly, which one is closer? This one is closer to this blue centroid. So I'm gonna classify it to blue, which is class 1. See it? The question is how to find this line. Because again, here I have only 2D. It's relatively easy. What if I have 3D? Then you're gonna have problem, because if I have 3D, there are too many possibilities. What I mean is this. Let me let me clear all. Every time I need to clear, that's something I really dislike. And I can go back. Let me write a new thing. Let me see. I think it's a field 3. Let me join this way.
If we have 3D,
I'm gonna have a plane.
Can we say that we have a hyperplane instead of a line?
No. If you have a 3D, you have a plane, a 2D plane. Why? Because 3 points give. Sorry, my fault. Sorry, that's exactly my fault. Sorry. I didn't make it very clear. What I mean is this. Here I have 2 features. I have 2 features and 2 classes, right? Okay. Yep. Now consider this. Suppose I have 3 classes, and in 3 dimensions, what's gonna happen? I can do it, let's say 3 classes in 10 dimensions. Why I said 3 dimensions? Because I cannot draw the 10 dimensions. That's why I said 3 dimensions. Okay. If I have 3 classes, what's gonna happen? Keep in mind that 1 class is gonna give you 1 point. See it? 1 point means 1 centroid, right? And if I have 2 centroids, via 2 points, I can draw what? I can draw a line, right? Then I can reduce the dimension from D dimensions to, for example, here I have 2 dimensions, 2 classes to 2 minus 1 equals to 1 dimension, right? D could be 100, okay? The reason, again, I put here as a 2D is because make my life easier. I can draw 3D as well. I wish I can draw 100D. It doesn't matter. As long as you have 2 classes, I can reduce it to a line. Because no matter in how many dimensional spaces, 2 points is gonna give you a line, right? Now, suppose I have 3 points. Of course, you cannot make it in 2D because 2D is gonna be something wrong. Suppose I have 3 points and I have 3D. What's gonna give you 3 points? Gonna give you what? A plane, right?
Yep.
Okay. Now let's try to play it. I don't know whether I can. Let's say plot. Plot plane 3 points, for example. Just make it for fun. Let's say I have x1, x2, x3. Okay, and then I'm gonna x equal to x1, x2, x3. Let's see, x2, x3. This I mean that x1, 2, 3 are the 3 points, okay? And they are, let's say they are column vectors. Otherwise, if they are row vectors, I'm gonna have a problem. I'm gonna use the fill3 functions, which is basically the same, but I'm gonna connect all these 3. And let's use red color, for example, and let's see. And I need to hold on, otherwise something's wrong. Otherwise, it's going to be gone. And I need X labels to make your life easier, because otherwise you cannot really see which one is which. It's going to be really, really dizzy, trust me. That's why I somewhat hate to build 3D systems. But here, I'd better let you see it more clear. This idea is really, really important. Okay, so if I draw this way, that tells me that, okay, let me just do this one. Okay. That tells that if I input 3 points, I'm gonna draw the plane, okay, in the 3D space, of course. Okay, then let's build one. Let me clear all, and let me build an x1 equal to what points you like? Give me 3 points. Whatever points you tell me, I can make it. So let's start from the origin. From both sides, give me another point.
5, 5, 5.
Okay, 5, 5, 5. Again, I need to make it a column vector. Okay, then Arab, give me the third one. Arab? You are muted, Arab. You are muted. I cannot hear you. Unmute yourself.
Okay, how about 1, 2, 3?
Okay, 1, 2, 3. Okay. Now let's. Yeah, I can hear you now. Mabuba already didn't work. Ask Mabuba. Okay. Huh? Why? Oh, okay. Wrong. Sorry. Yes. Okay. Here we go. And a bit ugly. Not my business. You guys suggested. Okay. Anyway. Okay. So clear. I have this 1, 2, 3 points, right? That's the 3 points that you told me. And see it? Suppose this is a feature space as 3, okay? So by these 3 points, see, I have a plane, right? The problem is what? Okay, let me suppose I'm looking at it, from the top, okay? So I'm gonna rotate under this system. The problem is that how would you build your system? Because a plane means what? Means a 2D, 2 dimensions, right? So from which direction would you look at this 2D? What do I mean? Say you can have this side, you can do it in this way. You can build your coordinate system in this way. Or you can build your coordinate system in this way. Let me change the color. Hey, come on. How to change? Oh, sorry. How to change the color? Let me undo it. Or you can build your coordinate system in this way. Let me use this color. And let me draw a line. Let me draw. You know what I mean? How would you build your coordinate system? You have infinitely many possibilities, right? You can rotate it, whatever. How would you see it? So why it is so important to determine how would I see it? Because you want to see at a direction that they different the most. Let me show you an illustration here. Oh, come on, clear all. It is something we're going to use later. So for example here, in this graph, suppose I'm going to see in this way, this direction. They are not too different, see it? Why? Because I mean, there are some big overlaps here. This indicates the frequency, okay? The density of 2 different normal distributions. But if I see here, then they're gonna be much more different. They're gonna be further, see it? That's the point. Although I know it's 1D, but which direction should I build my coordinate system? It's a big point. So I want to know this. Then I can really use the idea that I just introduced. Okay. So in other words, first, let's organize the logic here a little bit. First of all, suppose I have the feature space is D dimensions, okay? And suppose I have M classes. In most cases, you're gonna have D greater than or equal to M, or even D greater than equal to M. What I'm talking about is this. In most practical problems, you're gonna have something like this way. Then the problem is that for each class, I'm gonna have a centroid, right? So that if for M classes, I'm gonna have what? I'm gonna have M centroids, right? So this tells me that, hey, I don't have to really look at the data in this original D feature space. I can actually have a look at the data in the space that is spanned by these centroids. Question, I have M centroids here. What is the rank that I can span? In other words, how large is the space it's gonna be? Hint, suppose M equal to 2. I have 2 points. What is the dimension?
1.
1, right? From 2 points, you can build a line. You can draw a line. And it doesn't matter how many the D spaces. D can be 100. The reason, again, I showed the 2 is because it's easy to draw. Okay, suppose I have 3 classes. Then what is the rank of the spanned the spanned subspace? It's gonna be 2. Why? Because from 3 points I can build a plane, right? Similar, if you have 4 plane, if you have 4 centroids, you are gonna span a subsystem, a subspace to be what? To be rank 3. Okay. So in general, here, these M centroids lie in an affine subspace because I need, again, something like, a linear, or let's say a hyperplane of at most M-1 dimensions. So you may ask me, so why at most M dimension, -1 dimensions? Why don't you claim equals M-1? Because, for example, suppose what if 3 centroids, they happen to be in the same line? You know what I mean? So if they happen to be in the same line, in other words, I only need 1 dimension. I don't need 2 dimensions at all. That's why I said at most M-1 dimensions. Okay. So in other words, it doesn't matter how large your D is. I can always require only M-1 dimensions to represent your data and do the classification correctly. See the point? Why do the classification correctly? As proved here. Come on. As proved here. I've proved that they're equivalent. Why at most M-1 dimensions? Because it is corresponding to the subspace spanned by the M centroids. Clear? This is our logic, our idea, okay? Make the idea clear first. The next step, anyway, any questions first? Where's Saeed? Maybe he dropped. Anyway, he might feel, oh, it's really interesting. I'm gonna refer more books. Anyway, any questions so far? Make sure you understand the question, the idea. This idea is extremely important, much more important than the mathematics after it. Okay, now the question is how to do it. Because as I mentioned here, for example, here's 2D, you have infinitely many possibilities. Which one would you really find, right? And this, in other words, how to make it to convert it to a mathematical system or a mathematical model. Here, we're going to introduce Fisher's linear discriminant. So a very, very fundamental idea is this. Well, you have this kind of centroid. I'm going to find a direction such that your centroid, it's going to be, separate the most, right? So in this case, use a term of statistics. This is to maximize the between class covariance. Oops. Clear. To maximize the between class covariance. So the between class covariance is to measure the dispersion between different classes. Okay. So by the way, have you learned this one, the between classes versus within classes variance? If you have learned ANOVA, you're gonna see. Also by Fisher, this guy really likes this, and most of these are really, really amazing works. Okay, so for example, the between class variance formally it can be defined in this way. Okay, where your pi k is the prior distribution, and the mu k is what? Mu k is the centroid of class k, and mu is the overall mean, the mean of all the data. Okay, so I'm gonna maximize this one, and this B is the between class covariance matrix. Then I'm gonna see what value is the between class. In other words, I'm trying to find a direction, which means a vector A in the D-dimensional space, such that in this direction, my between class variance will be the maximized. Okay, once this one is maximized, then I'm gonna say, hey, this direction is really a very, very good direction. I may have a look at this direction. See it? However, there's a problem. This intuitive method is smart, but it is a problem. For example, have a look here. From this picture, you just want to maximize the between class variance. The question is, what if I have a lot of overlaps? For example, here, yes, the between class variance, it's relatively far, correct? If you look at this direction, you know, so it's going to be here. That's going to be something like this, from here to here, and this is from here to here. It's big. But see, if you look at this direction, you are going to have a lot of overlaps for these two classes of data. Once of overlaps, I may have problem. Why? If some data are, my target data is located in this area, it's going to cause the difficulty for me to predict which one, right? Which means it's going to reduce the accuracy, prediction accuracy. So what I need is actually to make a kind of like a balance, a trade-off that first, I want my between class variance to be large. And second thing is that I want to kind of like minimize this kind of within class variance, right? In other words, I want to, yes?
Yeah, is it like MANOVA or ANOVA concept?
What concept?
ANOVA or MANOVA?
Yes, yes, it is the same idea. Why? Because from the same person.
Okay.
All of these are from Fisher. Yes.
Okay.
So in other words, what I want to do is that I want to make a trade-off. On one hand, I want to maximize the betweenness. Sorry, I want to maximize the between class variance. On the other hand, I want to minimize the within class variance. So how to express it mathematically? A simple way is this. Instead of maximize this part, I'm going to maximize this part, which is a ratio of the between class variance versus the within class variance. This B, as I mentioned, is the between class covariance matrix, and this sigma is our sigma. In practice, you can estimate this sigma by sigma hat, you know, using this way, using 6 again. Where's my 6? 6, 6, 6 is here. Okay, so of course, I assume this B and the sigma is known here. Why? Because I can easily calculate it. Okay, so the question is, can I find a direction such that I call it relative, you know, the relative between class, or let's say the between class variance relative to the within class variance as maximized. And it's easy to see that this problem is equivalent to this problem. Why? Because A is just kind of like a scalar, you know what I mean? I can use A times, you know, the norm of A. In other words, in this way, I'm gonna normalize the numerator, normalize the denominator to make this one to be 1. And I just need to do this one. You know what I mean? It's something like I use this one divided by the norm of itself, so that the denominator is going to be 1. Make my life easier. And this is nothing but the Rayleigh quotient problem. Habuba, remember it?
Yes.
In June and May, you have something research on this.
Yes.
And we applied what? We applied something like the QA factorization to do this problem. That's one way. In the following here, I'm not gonna use the QR factorization. One reason because I haven't taught it yet. The second reason that I'm lazy to draw the figures. You're gonna draw a lot of these kind of things. I'm lazy to do this. I'm gonna use the algebraic way, which is easier. This we can use the KKT. Guys, I hope you think about this by yourself rather than have a look at my solution. This problem is a very simple problem. All of you should be able to solve it, as long as you have learned KKT. You just need to play some tricks. Very simple. By KKT, what do I have? I have the stationarity condition, right? Which is nothing but the the nabla with respect to this A equal to 0. I mean, plus this part, right? Because this part is an equal dimension, equal constraint. So I think to make it easier, I directly write the Lagrange function, and I define the Lagrange function in this way, minus lambda rather than plus lambda. Why? Because this is a maximization problem. So I use the minus lambda. Okay. So equivalently, you can say, okay, I'm gonna make the gradient with respect to A to this Lagrange function, and the KKT condition tells you what? This equal to 0 vector, okay? So I have 0 equal to, you just do this one, make the gradient with respect to A. What do you have? So this gives you, 2A, right? And this gives you 2 lambda sigma A. And so that you have this part. You have this. And this equals to 0, super simple. You directly have this and this. To summarize it, this KKT condition gives me this, sigma inverse BA equal to lambda A. And guys, what is lambda and A here? From this expression, you should be able to recognize it immediately. What is that? Eigenvalues and eigenvectors, right? Lambda is the eigenvalue, A is the corresponding eigenvector of what? Of this matrix, sigma inverse B, right? Suppose this is the matrix, whatever, for example, matrix M. Then I have A as the eigenvector and lambda as the eigenvalue of M, right? However, don't forget that KKT is what? Is a necessary condition, okay? KKT is clear and okay. KKT is a necessary condition. This just tells you that, well, if A is really the optimal solution, then A must be what? Must be an eigenvector of sigma inverse B, this matrix. The question is, how many eigenvectors do I have? Suppose it's a full rank, then how many eigenvalues do I have? I have D eigenvalues. Which one should I choose? This, again, KKT is a necessary condition. It just tells you that, well, if, for example, A star, I use A1 here. If A1 is the optimal solution, then A1 must be an eigenvalue, eigenvector. Of course, that's correct. But which one, right? We want to find exactly which one. To this end, first, let me make my life easier. I assume my lambdas, the name of lambdas are this way. Lambda 1 is greater than or equal to lambda 2, blah, 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 greater than or equal to lambda D, okay? Now, let's have a look at this objective function. ATBA, see it? What is ATBA? Because BA equal to this, right? And let me draw up an arrow. BA equal to this. So I can plug in, this becomes lambda AT sigma A. See it? Lambda AT sigma A becomes what? Becomes lambda. Why? Because of this, come on, undo, how to erase. Because I have this one.
This value is 1.
Yes, that's what I'm talking about. But stupid, I have to handle with the computer. Here and here. This one equal to 1. That's the reason why AT sigma A equal to 1. So this is equal to lambda. And immediately get a solution. Why? Because you want to find a lambda such that this one is maximized. And finally, what is the value of this? This is lambda itself. So which lambda should you choose to maximize it? You're going to choose the maximum lambda.
Maximum eigenvalue.
Right? Exactly. Very, very simple, right? Okay. Question, what if this is a minimization problem?
Lambda D.
Yes, exactly. The same, okay? That's how you can see in many this kind of books or papers say, Rayleigh quota, blah, blah, blah. And there are some very, very difficult QR factorizations. You don't need, just use KKT, 2 steps done. Super simple, everybody can understand. Okay, so that's the point. Okay, now we have already successfully find all these, sorry, not all, the first A1. Okay, which is the maximum, which is exactly the solution, optimal solution to this problem, which is equivalent, equivalently the optimal solution to this problem, right? Everything looks good. Guys happy? But there's a problem. What is the problem? The problem is that I said that I want to convert the 2D to up to m-1 dimensions. But here you just found the first one. Suppose your m equal to, suppose for example, I have 3 classes. I need to have 2, right? How to find the second one? That's a problem. And now let's recall, what are these A's? These A's are, again, the directions from which I want to kind of like which direction, for example, here in this, come on, let's come back. Here, for example, in this plan, I want to find a direction, for example, something like this way. No. Redo, clear all. I want to find something like this way. For example, a coordinate system like this, okay? So this is what? This is something, a spanned subspace by these 2 centroids, right? So usually for a spanned space, what do? We assume that different vectors in the spanned space, they're what? They're orthogonal. See it, right? It's just like our regular Euclidean system, the coordinate system as well. Your x, y, z, they're orthogonal to each other. Okay, so that without the loss of generality, we can assume that suppose I have the first vector, the first direction is a1, the second direction is a2, the third direction is a3. I can assume that all of them are orthogonal. And the second thing is that suppose you already have a1, okay? You have a1 already. You want to find an a2, which is orthogonal, but it's not enough. You want to find a2 that among any vector which is orthogonal to a1, you also want to make this one to be maximized, right? You want to make this to be maximized. In other words, to solve a2, I'm asking, hey, is there an a such that this a is vertical to, it's perpendicular to a1, and this is also maximized. Now suppose you have already got a1 and a2. For a3, you're asking, hey, is there an a such that it's perpendicular to a1 and perpendicular to a2, and meanwhile, this one is maximized, right? And blah, 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 you can do it to am-1. And this is exactly what? QA factorization. But here, let's forget QA factorization. Let's directly use eigenvalue decomposition to see whether I can get the answer. The reason is yes, I can immediately get the answer. Again, it is because this matrix sigma must be a what? A positive definite matrix. In other words, all the lambdas must be greater than 0. In other words, all my lambdas must be greater than 0, and hence what? All the vector space. Sorry, my logic is wrong. Sorry, I should say in this way, because this because this covariance matrix is PD, so I must have eigenvalue decomposition. And hence, the V space, remember, I make it to be this way. The V space here, come on. The V space, where's my eigenvalue? Here. The V space here must be orthonormal. That means that different Vi and Vj, they must be orthogonal. So you immediately get the solution. Why? Because what you need to do is only to find the second eigenvector, which makes this one the maximum. I would say the eigenvector which makes this one the second maximum, because the first maximum is A1. You've already got it, right? And you can guarantee that, suppose I name this one to be A2, okay? You can guarantee A1 and A2 must be orthogonal. Why? Because eigenvalue decomposition. I must have the eigenvalue decomposition. And by definition, my V spaces are what? Are orthogonal. Similar, A3 must be the what? The third eigenvector that maximizes this one, right? And how to find, let's say, the first, the second, the third eigenvector? Very simple. You just need to find the biggest eigenvalue, the second biggest eigenvalue, the third biggest eigenvalue, and find the corresponding eigenvectors. In other words, suppose you have a vector D, and you have a matrix. You have what? You have a left matrix V and a right matrix VT. What I'm talking about this. Let me write it down here. Okay, suppose you have, I really hate this. Anyway, suppose you have a matrix. How to insert a matrix here? suppose you have a matrix. Okay, to make my life easier, I just draw it 3 by 3. Okay, excuse me, please. So okay, wait. Suppose you have a V matrix equal to V1, V2, V2, and V3. Okay, and the right side is the T of this one. Okay, and suppose you have here lambda 1, lambda 1, oops, lambda 2, lambda 3, excuse me. And as we mentioned, lambda 1 must be greater than or equal to lambda 2 must be greater than or equal to lambda 3, right? What you're going to do is simple. You're going to find the biggest eigenvector, eigenvalue, and the corresponding one, for example, is V1. And so this one will be your A1. This one will be your A2. This one will be your A3. That's it. Easy. So after doing this, and then I can claim that this n minus 1, what I use as G. G is something that you, how many coordinates that you really need. Okay, G must be less than or equal to n minus 1. Why? Because up to n minus 1. Then use this way, I can find all these AGs. Meaning what? Meaning the new system, we call it the discriminant coordinates. In this new discriminant coordinates system, all the vectors, all the data can be transferred onto this span space. Get a point? What I mean is that suppose I've already know A1, A2, AG, right? So this A1, A2, AG is gonna span a space, right? You know, are you comfortable with the term span space, spanning space? Okay, so in linear algebra, I think this way. Suppose I review, okay? My spanning space is this. Suppose I have, for example, A1 plus A2 plus AG, right? Oops, why every time this way? The spanning space is this, so that I can have, for example, the coordinates under this system as x1, for example, x2, and xg equal to what? Equals to your original space. Let me use y for example. Original space means in the Euclidean space, and times x1, a1 is a vector, times x2, a2 is also a vector, x1, 2, 3 times xg. x1, 2, 3, all these are what? All these are, sorry, a big mistake. A very big mistake. Great. Should be in this one.
So I think, according to the linear algebra, A1, A2 to AG, they span a subspace if they are linearly independent, and any other vector in this space can be written based on a linear.
Sure. Yes, this is spanning space. You're absolutely correct. And this is the case because why? Because I use this I use this system to span it. Okay. And okay, I think I wrote it here. So that if I write it in this way, then these y's are what? Are the coordinates of this, right? So that I can have, for a given data, I can have, the corresponding. I can have the no, it's wrong. Sorry, it's still wrong. For a given, let's say for a given x. For a given x, why have the x1? Control V here. All of this is x. Meaning that suppose I have data x, okay? What I'm gonna do is that I'm gonna make the inner product onto each new coordinate system. Then this tells you that in A1, this system, the coordinate would be this. This is called the discriminant variable. And in A2 direction, the coordinate would be this. In AG direction, the coordinate would be this. Okay, so after doing this, then yes, I can really convert the whole problem to these G dimensions. Again, G is less than or equal to M. Due to the time limit, I'm gonna finish this part in next lecture. And the next lecture, we're gonna start with SVM, okay, support vector machine. And Arab, for you, I'm gonna give you a midterm exam this Friday. No worry. Anyway, let's stop the video first. So that's all about the main part of the class, okay? Then I'm gonna